In this problem, we're told that x and y vary inversely, and then we're given one specific point that's part of that relationship. So this part, telling us that x and y vary inversely, tells us that we have a function that looks like y equals k over x. And then this part that tells us when x equals 2, y equals 8, then we know that if y is 8, then x is 2. So if I solve that for k, I can see that the constant of variation is going to equal 16. So for part A, when it asks us what is the function of the inverse variation, they're asking us for the function that includes the specific k value that governs the relationship. So y equals 16 over x. Then in part B, they ask us to graph the function. And you know that in pretty much every other lesson this year, I always want you to go back to a parent function every time you graph a function. The trick with these inverse relationships is that the k really does control the steepness. So there isn't a particular XY table that you can just always use, especially when you're dealing with inverse and you have division going on. I need to choose something that makes sense. So when I think about making an XY table here, I realize whatever I pick, I'm going to have to take 16 and divide by it. So if I want to divide evenly into 16, it would make sense to pick factors of 16. And like with other functions that you're not really familiar with, it really helps if you start by picking some positives and some negatives. Now, if you think for a minute, why aren't we picking 0? Well, if we picked 0, we'd be plugging 0 in for x, and we know we can't divide by x. So I just need some negatives and some positives, and I need those numbers to divide evenly into 16. So I might, if I start with my positives, try stuff like 1, 2, 4, 8, and 16 because we're not real familiar with this yet. So let's see what happens when I plug those positives in. Well, dividing 16 by any of those numbers gives me 16, 8, 4, 2, and 1. Now, if I start to do some negatives, like let's say we start with -1 and -2, notice I'm going to get the same numbers I had before, but this time it's just going to be the negative of all of those. So I probably don't need to keep going with that. I think you guys can kind of see where it's going. Now, this is going to be your first shot at graphing something like this. In the future, you're already going to have a pretty good idea of what the graph should look like, and that's going to make it a little bit easier. So I'm going ahead and I'm putting my axes in the middle because there's no translations here, so it is going to be centered around the origin. When I look at this, I see some values are kind of close to the origin, but notice my numbers get big really fast. So I might need to pick a scale that goes by 2s rather than going by 1s if I want to be able to fit very much on my graph. So if I'm going by 2s on both axes, here would be my 0.44. My 0.82 would be here, and my 0.28 would be there. And then those ones that are getting closer to 0, I'm not actually going to have to graph. I'm going to go ahead and sketch my curve in there. So here's my 0.28, my 0.44, and my 0.82. And then when I go to start graphing the other direction, notice I'm going to have -2, -8. But I would also have -4, -4, and -8, -2. It's like all the same numbers as in quadrant 1, except in quadrant 3. And the shape of the graph is the same. Oops, I missed. Shape of the graph is the same. Now, it's really careful how you draw that shape, and it's important to label some things. So first of all, we didn't use the standard scale. So without this slope, nobody would know what numbers those really were. But it's also important that it doesn't look like either of those branches of this graph is ever going to run into the x-axis or the y-axis, because those are each what we call asymptotes of the graph, lines that we get really, really close to, but we never actually touch. So really important that you don't make it look like those two sides run into the axes. That would be considered a sufficient graph. And then C asks us, what is y when x is 4? Now, we actually already have this because notice the answer to this is right here. Y equals 4 when x equals 4. We could get that information by looking at the graph. We could get that information by looking at the table. If we didn't have either of those things, we could plug back into this equation over here. We could say, well, what's y when x is 4? And we could conclude that it was 4, but we can tell from the work that we've done already. Let's take a look at number 3. Number 3 says your employer decides to hire extra help to deliver newspapers during the holidays. The table shows the number of employees who delivered papers each week and the time needed for delivery. What function models this problem? How many employees should there be to deliver newspapers in at most 40 minutes per week? All right, well, let's look at what's happening. As I look across the top, I see 2, 4, 10, 20, so that's increasing. And then as I look across the bottom, I see 150, 20, 10. That's decreasing. So that suggests this is probably an inverse relationship. And that makes sense. The more people I have doing the work, the less time any of those people has to spend doing that work. So I'm anticipating a y equals k over x scenario. So I'm just going to start by checking each of the possible constants of variation. So checking those x, y's. Well, x times y here is 200. Same thing here, same here, and same here. So that is consistent. This is definitely an inverse variation. So to start the work for part A, what function models this problem? We've just figured out what the constant is, and so we know we're going to have y equals 200 divided by x. So that's our inverse relationship. And then B is asking us to use that inverse relationship to answer some questions. How many employees should there be to deliver newspapers in at most 40 minutes each week? Well, that's a Y value, right? Because time in minutes is the effect. So I've got 40 equals 200 over x. And sometimes students get a little worried about the fact that that x is in the denominator. So it might actually help if you just make the whole thing look like a proportion. We can easily see that we want to cross multiply and then divide both sides by 40. Reducing that by 10, I've really just got 20 divided by 4. So x is 5. So they're going to need 5 employees.